In this video, we're going to discuss how to use experimental data to determine the rate law, and then how to use that rate law to determine the rate constant and how we get those units. So here is a reaction that we're given, and then here's some experimental data. Now these data would have to be provided to you because otherwise you would not be able to do this problem. So this is a pretty typical rate law determination type problem. You're given a reaction, you're given some experimental data. All right, so this is pretty much what you can expect to see. So here's our strategy. The first thing we're going to do is we're going to write a generic rate law, which comes from the reaction. Okay, rate is equal to K, which is the rate constant, times the concentration of NH4, that's one of my reactants, raised to the X, X is a value that we will solve for, times the concentration of NO2 minus, okay, to the Y. And again, you can use whatever variables here you want. If you want to use A and B or P and Q, whatever variables make you happy, that's completely your choice. But we're taking our reactants because this is the method of initial rates. So we're using our reactants. We're just putting a generic variable there and a generic variable there. We're not even concerning ourselves with these products. Okay, so don't let that fool you. Then what we're going to do is we're going to use our experimental data that we are given right here to solve for the values of X and Y. And then we're going to take the answer that we get here and then use our experimental data again to solve for K. So this is our plan of action. So the first thing I'm going to do is I'm going to solve for X. Okay, so the goal here to solve for X is you want to pick a trial pair in your reaction data where ammonium changes and nitrite does not. Okay, because we want NO2 minus to cancel out. Okay, so we need to make sure that this value does not change and this value does. So if you look at trials 2 and trial 3, NH4 plus changes, NO2 minus does not. Okay, that's the goal. If you're solving for NH4 plus, you need to pick a pair where this one is not changing and this one is changing. So now we're just going to plug into this is the rate law, right? Rate equals K, NH4 plus to the X, NO2 minus to the Y, right? So for trial 3, the rate is, trial 3, 5.4 times 10 to the negative 7th, which I wrote here in condensed form, 5.4 times 10 to the negative 7th, equals K, right? That's not a value we don't know yet, times 0.2, because that's the value for trial 3, to the X, times 0.01, running out of room here, to the Y, right? So literally all I did was plug these three values in, boom, 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 for trial 3, okay? And then for trial 2, I'm going to do the exact same thing. I'm going to put the rate. The rate at trial 2 was 2.7 times 10 to the negative 7th. There we go. K, we still don't know that value yet. 0.1 comes directly from the data, and 0.01 comes directly from the data. Now, when we do our math, if we divide this divided by this, gives me 2. K divided by K cancels, so that's gone. 0.2 divided by 0.1 is 2, and it's to the X, right? And then 0.01 divided by 0.01, that goes away. So what we're left with is 2 is equal to 2 to the X. So that means that X must be 1, right? Because 2 to the first power would be 2. Now, if you did, instead of doing 3 over 2, if you did 2 over 3, just note that you would still get the same value of X. Okay, so that's how we solve for X. And now we're going to do the exact same thing solving for Y. Except this time, when we're solving for Y, we want NO2 minus to change and NH4 plus to be the one that stays constant. So if we're looking at our data here, that's trial 1 and trial 2. Because you notice NH4 plus is constant, NO2 minus is the one that is changing. So we're going to do the exact same procedure we did last time. This is our generic rate law. Rate is equal to K, NH4 plus to the X, NO2 minus to the Y. So we're going to use trial 1 on top. So the rate for trial 1 was 1.35 times 10 to the negative 7th. That goes right there. Equals K. We don't know the value of K yet. 0.1 to the X times 0.0050 to the Y. And then rate equals K, NH4 plus to the X, NO2 minus to the Y. Now we're using trial 2. So the rate at trial 2 is 2.7 times 10 to the negative 7th. That goes right there. K, we don't know, 0.1. and 0.01. All right, now we're going to divide through just like we did again in the previous problem. This divided by this is 0.5. K over K goes away. 0.1 over 0.1 goes away. 0.005 divided by 0.01 is 0.5. So 0.5 is equal to 0.5 to the y. Therefore, y is equal to 1. And again, if you had done it the other way, if you had 2 over 1, your value of y would still be the same. So, from our previous problem, we determined that x was 1, and we just now determined that y is 1. So that means that the rate is equal to k times NH4 plus to the first. You don't have to write that 1 if it's first order. And NO2 minus to the first. Again, we can omit that. So that's my rate that I've determined, my rate law that I've determined so far. But now I need to determine the value of k. So to do that, I have to go back to my data again. All right, and so what we're going to do is we're going to pick a trial 1, 2, or 3. It does not matter which one you choose. Okay, you'll get the exact same answer either way, so it makes no difference which one you use. I just picked trial 2, just shoot for the middle, right? So I picked trial 2. Okay, and again, I just want to emphasize that any trial will work. So what we're going to do is we're going to use the data from trial 2, and we're going to plug it into our rate law that we just calculated. So if rate is equal to k times NH4 plus to the first, NO2 minus to the first, we would just say the rate at trial 2, 2.7 times 10 to the negative 7th. And then here's where we need to include our units. The units for the rate are moles per liter second. Okay, so I include that moles per liter second. Equals K, 0.1 moles per liter, and that's not being to the second or the third, it's just first order, times 0.01 moles per liter. Okay, because this is molarity, right? Molarity is moles per liter. All right, so when I start crunching the numbers, okay, this times this gives me this, and moles per liter times moles per liter is moles squared per liter squared. All right, we've got to watch our units here really, really carefully. So now to get K by itself, I just divide both sides by 0.001 moles squared per liter squared. And so that's what we get, right? K is equal to 2.7 times 10 to the negative 7th moles per liter second divided by 0.0010 moles squared per liter squared. So most students can do this part right here. This part, 2.7 times 10 to the negative 7th divided by 1 times 10 to the negative 3rd. Most students can do that, no problem. What gets students is the units, okay? When you divide a fraction, that's the same thing as multiplying by the inverse. So moles per liter second divided by moles squared liter squared is the same thing as moles per liter second times liter squared over mole squared, right? You flip it, okay? And then you multiply. So that liter goes away and that exponent becomes 1. That mole goes away and that exponent becomes 1. So my units are liters per mole second. Now one note I want to make here is let's pretend that this had been squared just for fun. Okay? If this had been squared, if NH4 plus had been squared, that would mean that my units here would be moles cubed over liters cubed, right? Because you'd have moles squared, liter squared times moles per liter. So if this had been squared, my units here would have been cubed, which means my answer would have liters squared per mole squared second. So the units vary based on what your rate law is. And I hope this problem helps you in using a rate law to determine the value of K.